Hello, welcome to a new video. Today we're going to do this problem called 700 search in a binary search tree. I just realized how my bunny ears look, but this is just for I just got done with my skin routine, so I'm just gonna keep this on. Anyways, so let's go solve this problem. This does look easy, but just like looking at it, I don't know how to code it. So if I don't know how to code an easy problem, then it's not easy for me. Because if I just look at the easy problem and then just read it, I can solve it just by looking at it. But for this one, I don't know how to code it, but we'll see. Let's just get started. So you are given the root of a binary search tree, VST, and an integer val. Find the node in the binary search tree that the node's value equals to val, and return the subtree rooted with that node, and such a node does not exist. Wait, if such a node does not exist, return null. Okay, so our input is two things, root of EST and then int val. Then our output is to return node of VST that has node.val equal to val. Right? So that's gonna make sense. And so yeah, is there any notes I need to take? I don't think so. Um so let's go over some questions, I guess. So like I guess what is min size of BST? I'm guessing it's 1. Let's check. It is, yeah, 1. And then I don't think the value really matters here in this case. So yeah, let's just get started. Let's go ahead and kind of go through an example. So let's say this is a binary search tree, right? So let's say I think start off with like 10, right? Wait, can you guys see this? Okay, you can't see that. Okay, so let's say we have this binary search tree 10, and this is like 5, I guess, and this is like 20, 3, and then 6, and then let's say this is like, let me put like this, right? Because we're not. That looks really bad, but anyways, it looks really bad. I think I can just use this, right? Like 5. Oh shit! Wait, this is so cool. Wait, this is so good. All right, yeah. So let's say they put it like that, right? And we want to find 5, right? So we start at the root, and we're doing binary search, right? So we're like, okay, so if current value less than so if current value is less than or more than the target value we're trying to get, go either left or right. And so in this case, since the current value is less than the target value, because we want to look for 5, right? We have to go left. So so do recursion, go left. And then there's also a base case where it's like if not no, if the node's null, then just return none. Like either way, this case where our current value is equal to the target value, we're going to return that node. So return that node back up here, and then return it back up to the original call. Then we get 5 from the call. So yeah, that's pretty much it. So that's a good example. But what if there's a case where I guess our target value is, I guess, 30, right? Let's say our target value is 30. So can I? Yeah, okay. Target value is equal to 30. Right, our target value is equal to 30, right? And so obviously, when we start off, we're going to go right. Go right. I don't like this. We're gonna go right. I think the color. Yeah, we're gonna go right, and then we're gonna go right again. We're at this 20. Like, okay, so this 20 is like okay, so is 20 more than or less than 30, our target value? It is less than. Right, so since 20 is less than, I mean, since the target value is more than 20, we have to go right. So we go right, and then we're at the point where our base case is like, okay, so we're null, so just return null. So we're gonna return null, here, and then 20 is going to return null, and then 10 is going to return null. So yeah, basically it. Right, so yeah. Gotta make sense, right? And so from that point on, we kind of went through the two examples where we're gonna reach the base case for each. So I think we can just go into a plan. And we can go to a match actually, just to reiterate what I was trying to say. So, um, as I was going through that example, we're kind of referencing recursion, mostly that first search. Um, and then we're gonna have some base cases like if null or if equal to val for the target, stuff like that. Um, and then we're also gonna go left and right, depending on BST, binary search. Oops, binary search. And then what else? That's pretty much it. Just basically binary search. So let's go ahead and plan. Let's go through some pseudocode. So first thing I want to do in my code is I want to initialize the first search. And while I do that first search, we're obviously going to take in a node. Right, that's basically it. And then for our base case, we're going to say, so base cases and such that we're in a case where the if node is null, and just return null. But if the case is such that if the current value, if val is equal to target, then just return node. But if that's not the case, then um, so if I guess I could say elif, right? Elif. Um, so I like else if better actually. So else if target is more than no.val. Oops, why did it run? If target is more than no.val, then that means from the node we have to go right. So DFS right, and then else else target is less than no.val, then go right. I mean go left, and then in the end we're going to return. Well, actually, I think I just returned this, right? Is that right? I'm pretty sure that's right because I'm pretty sure I just add the returns at the end, no, at the beginning, or yeah, I mean in the left or right, right? Mostly because um, whenever we call this, let's say, I mean, let's say our target is like, I'm trying to justify because I don't really do this stuff. So let's say our target's 5, right? So we go left, and then as we go left, we're like, okay, so go left and then return whatever this returns, right? And so we're like, okay, we're at this 5 now. This base case, it skips the null base case, but it runs through this base case where if the node dot val is equal to target, which is 5, then the return node. So this returns a node, and then we're back at this 10, right? Because the 5 returns to the 10. And 10 like, okay, so I got called this, so I'm going to return whatever this is, which I just called. So then 10 to return 5, the node, I guess. So that makes sense, right? So then once we do that, we're just going to return the EFS of roots, right? And then that's basically it. So I'm pretty sure that's it, I think, hopefully. Let's just kind of go ahead and code it. I'm pretty sure it works. I just did an example with it, and it does look like it works while using the pseudocode itself. So let's just try it out. So if it's not, then I'm going to be really disappointed in myself, and then I'm going to have a lot of fun. So let's just shift tab that so it looks nice. And it's kind of, let's go over our plan and just copy it and kind of say it in words. So first thing my plan I want to do is I want to find a function called DFS and take a node. And then we're going to do the base cases. So base cases. So the base case where if not node, then return none. But if it's the case in such, wait, can you guys see what am I writing? Okay, I think so. Let's watch the video over. I don't think, wait, can it? Okay, cool, you can. It's just like, it's just weird. Like, there's so much space. I don't know. So if not node, then return none. But if it's the case, oops. What? But if it's the case where if node.val that we're at right now, or current, is equal to the target, which is val, then return node, and then else if, or I'm pretty sure it's elif. Yeah, elif target val is more than node.val, then go right. But I also say to just return whatever that returns. Um, else where else we just return DFS no.left. This should work. So just go ahead and before we run it, we also got to make sure to call DFS and return whatever that calls or that returns. So run and it fails. All right, it runs. Submit and it runs. Let's go. Let's go. Let's go. Let's go. Let's go. All right, so yeah, pretty simple. I just had to think about it because I don't really do like return the call. I usually do like something like this where I say like where node where node is equal to that, and then at the end of DFS I just say return node like that, right? That's kind of what I do, but it makes sense once because I'm getting used to recursion and stuff like that. That's kind of why I'm doing this LeetCode 75. So whenever I whenever I come across a problem in an interview like this, I'm pretty comfortable. So it's a good thing that I tried this out. Makes sense to me. So yeah, pretty much it. Yeah, for the complexity, it's O of n. We go through every node once in a binary search tree, and for space, it is basically O of 1. We don't really do anything. We don't create a list. We don't use a data structure like a queue or stack. So yeah, that's pretty much it.